All right, so we're going to continue our conversation on potential energy diagrams and talk about a specific feature which is called enthalpy. Enthalpy is a measure of the heat content of a substance. So, in chemical reactions, this heat is due to potential energy stored in bonds. So, you'll see that key word, potential energy is the heat. Okay, so energy is measured in joules or kilojoules, heat is measured in joules or kilojoules. And this potential energy is stored as heat or potential energy is stored in chemical bonds and can be released as heat or absorbed as heat. And this will happen when bonds are breaking or atoms are rearranging and new bonds are forming. And then this cause there'll be a total heat content of your substance called its enthalpy, and then it'll lead to enthalpy changes, which will be equivalent to the changes in potential energy. So the equation that we're going to use is delta H, or change in enthalpy, is equal to the heat content of your products minus the heat content of your reactants. So let's look at this on a potential energy diagram. Let's start with an exothermic reaction. So you have an example here. It's a potential energy diagram over time. And you've got your reactants, you've got your activated complex, you'd have your activation energy that is required to reach your activated complex for a successful collision, and then over here you'd have your products. Now there's a heat content in the system. At the beginning, your reactants have 75 kilojoules of energy, or 75 kilojoules of potential energy, and your products have only 25 kilojoules of potential energy. So let's look at how much heat was either absorbed or released. And the easiest way to do this is to do your calculation. We've got delta H is equal to the heat of your products minus the heat of your reactants. Now, the heat content of your products is 25 kilojoules. The heat content of your reactants is 75. So overall, your change in enthalpy, or your change in heat, is negative 50 kilojoules. Now, what does this mean? Well, it means that if you looked at your graph, the heat content of your products is less than the heat content of your reactants. Now, if you don't like less than or greater than signs, just write the word less. So the heat content of your products is less than the heat content of your reactants. So your change in heat, or your enthalpy change, came out as negative, which means that heat did what? Well, you had 75 kilojoules, you ended up with 25. What happened to the other 50? Well, they were released into your surroundings. So the surroundings will feel warmer. So when you have an exothermic reaction, the heat content of your products is less than your reactants, meaning that heat was left, or heat left your system. Okay? On a potential energy diagram, this looks like a step down because the reactants are higher than the products. Now, if you're showing an exothermic reaction in an equation, there's two ways of doing it. One is you'd simply have reactants go to products, and then outside of the equation, you'd have a delta H, and your delta H you would write as negative 50 kilojoules. And it is known that if a delta H is negative, that this was an exothermic reaction. The other way of showing this is actually to include the heat as a reactant or a product. Now, because heat is released, you would include it as a product, and you'd be adding 50 kilojoules of heat to the product side, showing that that 50 kilojoules was released. So when you're putting it as a product, you put plus 50 kilojoules, but if you're writing it as delta H, you would put negative 50 kilojoules. The other thing we like to do is also include this on our potential energy diagram. So up here, I would also show an enthalpy change by having an arrow going between my reactants and my products. So when it's exothermic, I like to put my arrow going down, showing that heat is released. And you would put delta H is equal to negative 50 kilojoules, and you can include it in your diagram. Now, there's no standard with this. I've done it over here with reactants to products. Some people will go here to here and put delta H is equal to negative 50 kilojoules. All that really matters is that you know it's the difference between reactants and products, and that if it is exothermic, it's a negative energy. All right, so let's do the exact same thing for an endothermic reaction. If you feel like you've got it, feel free to pause the video and do it. But we're going to go piece by piece. So for this one, when we look at it, we've got my reactants, and the heat content of my reactants is 25 kilojoules. And then over here, you've got your products, and the heat content of my products is 50 kilojoules. So if I was going to calculate delta H, it's the heat content of the products minus the heat content of the reactants. So it would be 50 minus 25, which comes out as positive 25 kilojoules. Now, why did this happen? Well, in this example, the heat energy of the products was greater than the heat energy of the reactants. So if you don't like those signs, again, you can just write the word greater. So my delta H came out as positive, and what that means for my system is that heat energy was absorbed by my reaction. I went from having 25 in the beginning, and at the end of my reaction, I had 50, which means my delta H was an absorption of energy, and specifically 25 kilojoules in this example, which means that if you're taking heat energy from the surroundings will feel cooler. On a potential energy diagram, this looks like a step up, right? Reactants are down here, products are up here. And just like an exothermic reaction, there's two ways of showing that this is an endothermic reaction in terms of the equation. You would have reactants going to products, and then delta H on the outside, you'd have a positive 25 kilojoules. You do not need to show the positive sign. I'm just doing it to prove a point, right? So if you actually answered as just 25 kilojoules, then you're totally fine. I'm just showing the difference between an exothermic being negative and an endothermic being positive. If you were to write it in terms of a reactant or a product, because the energy is being absorbed, it's one of the reactants. So you'd be adding 25 kilojoules of heat energy to the reactant side of the equation, and then there'd be nothing on the products. All right, go and give enthalpy a go.